What is this thing we call iron? What is the difference between cast iron and steel? By watching this video, we will explore and understand the iron and steel casting processes in detail. Are you ready to learn everything from crystal structures to compositions? First, let's take a look at the iron casting process. Iron casting occurs by melting iron ore at high temperatures and pouring it into molds. This seemingly simple process is actually very complex and involves various methods to produce different types of iron. Iron is characterized by its crystal structures. These structures are formed by the arrangement of atoms and determine the physical properties of iron. For example, different crystal structures, such as alpha iron and gamma iron, have a significant impact on the hardness and strength of iron. For instance, alpha iron has a body-centered cubic structure, while gamma iron, also known as austenite, has a face-centered cubic structure. With cooling over time, gamma iron turns into alpha iron. Now, what is the body-centered cubic structure, BCC, and face-centered cubic structure, FCC? And what difference is there? Let's discuss these. Let's start with the body-centered cubic structure. Consider a cube with a side length of 1 unit. The atoms within each cubic cell are arranged at the corners and center of the cell. In this configuration, each atom occupies a portion of the volume inside the cell. The atoms positioned at the corners and center of the unit cube form the body-centered cubic, BCC structure. An atom in this structure is in close proximity to neighboring atoms because there are atoms located at both its vertices and its center. The body-centered cubic structure typically exhibits greater hardness and durability because the atoms are densely packed. In contrast, in the face-centered cubic structure, atoms are situated solely at the corners of the cell. The interior of the cell remains vacant, with atoms arranged along the surfaces. As atoms are only present at the corner points, contact between atoms occurs solely along the surfaces. Consequently, the proximity between atoms in FCC is less than that in BCC. With atoms solely positioned on the surfaces, the crystal structure is less dense, spreading across a larger volume. So, how do the atoms in gamma iron change their cubic structure and become alpha iron? One of the main factors driving this change is temperature. Temperature plays a significant role in transforming the crystal structures of metals. At higher temperatures, the atoms in the metal possess more thermal energy, enabling their crystal structure to rearrange. This temperature is known as the critical temperature. As the metal cools from high temperatures to lower temperatures, the atoms lose thermal energy, leading to potential changes in the crystal structure. Temperature is a primary determinant of crystal structure. At higher temperatures, the face-centered cubic, FCC structure, such as austenite, is more stable because atoms have greater thermal energy supporting this structure. However, at lower temperatures, the body-centered cubic, BCC structure, like ferrite, becomes more stable as atoms possess less energy, and the BCC structure prefers a lower energy state. Of course, producing iron or steel is impossible without considering carbon. Carbon is one of the crucial components of iron and steel, and it significantly influences the transition from FCC to BCC. In alloys with low carbon content, the FCC structure typically remains stable. However, in alloys with high carbon content, carbon tends to stabilize the BCC structure. Hence, carbon content can impact the alloy's transition from FCC to BCC. Additionally, pressure and other environmental factors can also influence the crystal structure. Particularly under high pressure, the BCC structure may become more stable in certain cases. Cast iron is an alloy primarily composed of iron and carbon, along with various alloying elements. It is known for its high melting point, good fluidity and casting properties, as well as its high hardness and brittleness. Iron is the predominant component of cast iron, forming the matrix structure. Carbon, ranging from up to 2.14% to 6.6%, is another key element determining its properties. Low-carbon cast irons typically contain around 2.14% carbon. Cast iron is often fortified with alloying elements like silicon, Si, manganese, N, sulfur, S, phosphorus, P, chromium, Cr, nickel, Ni, molybdenum, Mo, and copper, Q. These elements can enhance mechanical properties, corrosion resistance, and other characteristics. The composition of cast iron varies depending on its intended use, casting method, and industrial requirements. Grey cast iron, for instance, features a graphite-reinforced matrix and typically contains between 2% and 4% carbon. Other varieties include white cast iron alloyed with chromium and molybdenum, and nodular cast iron alloyed with magnesium and/or cerium. Now that we understand the basic science behind it, let's take a look at the steel casting process. Steel is produced by alloying iron with carbon in specific proportions. When manufacturing steel, the amount of carbon used is much lower compared to cast iron, typically ranging between 0.05% and 2.14%. Steel is generally categorized into three classes based on carbon content: low carbon, medium carbon, and high carbon. Low-carbon steels typically contain carbon between 0.05% and 0.30%, medium-carbon steels between 0.30% and 0.60%, and high-carbon steels between 0.60% and 1.60%. By combining this alloy with precise proportions and employing appropriate processes, steel can attain its desired properties. Steel casting is a widely utilized method in the industry, and steel can be alloyed in a wide range by the addition of different elements. These alloys play a decisive role in the hardness, strength, corrosion resistance, and other properties of steel. For example, stainless steel is made resistant to corrosion by alloying it with chromium. Consequently, iron and steel casting are critical processes that form the basis of metallurgical science. Understanding these processes allows the production of more durable and efficient materials. We believe that in the future, these processes will be further developed with innovations focused on sustainability and efficiency. I hope this video has provided you with insight into the complexity of iron and steel casting processes. Remember to subscribe to our channel for more engaging content. Until next time.